Welcome. This is another technical technician video from Diagnation. This is going to be a quick video. Basically, we're just going to talk about TTL transistor to transistor logic and a micro clamp. We're just going to be looking at 3 channels. As you can see, as you zoom in on the schematic, you can take a snapshot of this. We have a channel A. We're looking at voltage at the alternator at the regulated terminal. Honda refers to that as FR. I believe that to be field regulation. And that circuit is wired right back to the PCM. You can see I have a FR denoted there at the PCM for field regulation. It is a duty cycled signal. The PCM will push 5 volts out to the regulator. The regulator will, from what appears to be, will toggle the 5 volts to create a duty cycled signal, which we will see on the scope. As we can see, between the PCM and the regulator is a connector, and we're going to see what happens when the connection opens up, when we have a duty cycle signal between one component to another that's transferring some type of information or validation or logic between modules or components. So you can see the 3 channels. Blue is at the regulator, green is at the PCM. Those are voltage, and the micro clamp is B, that is clamped onto the circuit. So basically, let's go to the scope and see what we have here. We will start the car and we'll talk about what a normal circuit looks like. Let's get locked in here. Okay, I will start the car. And we'll take a look at our action, what's happening. Okay, I know we're thick and red. I have to filter that. Everything will make sense when we get filtered. We're just running between the alternator and the PCM. This is just one circuit in this. There's many more circuits involved in this alternator. I'm just concentrating for this video on the one circuit. Obviously, there's powers, there's grounds, there's charge lights, there's network, there's other forms, there's ELD, electronic load detector, and other circuits on a Honda charging system. But basically, we're just looking at this one wire, and we're going to make and break the circuit, and then kind of look at your connector between the PCM and the alternator. Now, if that thing ever broke circuit for a few milliseconds, we'll see what would happen. So now I'll stop the scope and stop the car, and we'll analyze it. Okay, take a look at our circuit. We got a few frames. We're at 500 milliseconds per division. We got 3 mega samples. Our sampling rate per screen. I'll just roll it back to the beginning. Basically, we'll see what normal looks like about right here. Let's zoom in. Basically, we have our duty cycle signal. We can see it. You can see it in blue. Is the signal at the PCM. The green is at the alternator. In a good world, in a good circuit, they should be identical. That is the same circuit, the same piece of copper. Nonetheless, in red, we see current flowing. When the PCM in this case pushes the 5 voltage toward the alternator, and the alternator will use its transistor to tap the signal to ground on and off. Basically, it looks like it's controlled through a duty cycle. As we can see here, we're looking maybe about 60% on the ground side from the naked eye. I won't measure it, but then again, you can see. And when the alternator grounds its transistor to let the 5 volts go low, how much current are we flowing? We can see it right here. It's very little. I'm sorry, wrong channel. There's a millivolt to milliamp conversion with this clamp. So basically, we're looking at about okay, that's 2.6 millivolts, which is 2.6 milliamps. So nonetheless, let's see what happens when the circuit gets opened. I will go down the screen. The circuit gets broken about right here, and we'll see. We can take a kind of look at both. Obviously, here's where our circuit gets broken, and you could see the green, the blue, and the red. The red is current. The green is voltage at the PCM. I'm sorry, the green is at the PCM. The blue is at the alternator. Actually, the alternator regulator, to be specific. And the current clamp is clamped around the wire between the PCM and the alternator. We can see when the circuit breaks, current stops flowing. So, but yet our voltage at the PCM has the 5 volts. Obviously, that's where it's coming from. Okay, so it's no longer can push that it can push the voltage, but the circuit is open, so current will not flow, and the alternator goes low, as you can see right there, to about that's like 42 millivolts, but that's low. And when the circuit continues, when the circuit comes back again, when the contact and continuity is good, we can see current flowing, and we can see our duty cycles are mirroring one another, which they should be. That's the same circuit, green and blue, and basically we have current flowing again. You can see it right here. So it just kind of proves out that that the microclamp is a powerful tool, and then it can tell us so much, whether it be sensors or logic or networks. It's a really good indicator that the circuit's complete, and in this case we kind of know which way the current is flowing. We have the arrow from the microclamp pointing from the PCM to the alternator, and when the circuit breaks, you can see the alternator, the PCM has the high voltage, and the alternator has the low voltage, which would validate that that's the way the current's flowing. It's going from the PCM to the alternator. Anyway, take a look at this. I'll just zoom in one more time. We can see our current, we could see our voltage, and we can see that when the circuit opens, that we have no current flow. Anyway, this is Technical Technician signing off. Hope you enjoyed the video. Thank you very much.